Far beyond the quiet glow of our night sky, two vast spiral galaxies move through space together, bound by gravity and time. One of them is the Milky Way, the galaxy we live inside. The other is Andromeda, a distant presence that appears calm and almost insignificant from Earth, yet stretches across space in ways that are difficult to truly imagine. From our position inside the Milky Way, everything feels endless. Stars surround us in every direction, dust clouds drift between distant suns. There is no visible edge, no clear boundary where the galaxy stops. Andromeda, by contrast, appears contained, a faint blur suspended in the darkness, something that looks small simply because we are far away from it. But this sense of scale is shaped entirely by perspective. Galaxies are not objects with clean borders. They do not end where the light fades. They are layered structures made of stars, gas, dust, and vast halos of invisible matter, all held together by gravity across enormous distances. When we talk about the size of a galaxy, we are not really talking about diameter. We are talking about influence. Both the Milky Way and Andromeda are surrounded by enormous halos of dark matter and gas that extend far beyond what we can see. These halos are so large that they already overlap. The space between our galaxy and Andromeda is not empty. It is shared, shaped quietly by the gravity of both systems at the same time. Andromeda is often described as larger than the Milky Way, and in some ways it is. It contains more stars. Its visible disk extends farther. Its central bulge is larger and brighter, filled with older stars that hint at a long history of mergers and growth. But the Milky Way is not small. Its mass, once invisible matter is included, may be closer to Andromeda's than it first appears. This is where the idea of size begins to soften. Is a galaxy larger because it shines brighter, or because its gravity reaches farther? Is it bigger because of what we can see, or because of what we cannot? At these scales, size is no longer a single number. It becomes a relationship between mass, motion, and time. If this kind of calm, slow exploration helps you relax, you can subscribe to Theories Before Sleep and let the universe keep you company. Andromeda and the Milky Way are not just neighbours drifting past one another. They are moving together, slowly and inevitably. Over billions of years, they will merge into a single galaxy, long before any dramatic collision ever occurs. Their halos will blend, their gas will interact, and their stars will be rearranged by gravity in a process so slow it feels almost peaceful. To understand how big Andromeda really is compared to the Milky Way, we need to let go of simple ideas like edges and borders, and instead think in terms of influence, mass, and the quiet pull of gravity across time. Only then does the comparison begin to make sense. When astronomers try to compare Andromeda and the Milky Way in a serious way, the first thing they have to decide is what exactly they are measuring. This sounds trivial, but it isn't. A galaxy is not a single thing, it is a layered system, and each layer tells a different story about scale. If you look only at visible stars, Andromeda immediately appears dominant. Its stellar disk stretches farther into space than ours, with spiral arms that extend outward in a broad, elegant sweep. The Milky Way's visible disk is impressive from the inside, but measured objectively, it is more compact. Andromeda's disk is wider, flatter, and more luminous, meaning it contains a larger population of old bright stars spread over a greater area. In terms of sheer star count, Andromeda likely holds more than 1 trillion stars, while the Milky Way is estimated to contain a few hundred billion. That difference alone makes Andromeda feel enormous, but star count is a deceptive metric. Stars are not evenly distributed, and brightness does not correlate perfectly with mass. Many of Andromeda's stars are older and less massive, packed densely into its bulge. The Milky Way, meanwhile, has ongoing star formation in its spiral arms, and a different balance between young and old stellar populations. When you compare the total mass locked inside stars alone, the gap narrows. Andromeda still leads, but not by an order of magnitude. Then comes the bulge at the centre. Andromeda's central bulge is significantly larger than the Milky Way's, both in size and in mass. It is a dense spheroidal region filled with ancient stars orbiting a supermassive black hole that outweighs our own galaxy's central black hole by a wide margin. This bulge suggests a more violent past, one shaped by mergers and gravitational upheaval early in its history. In visible light, this bulge dominates Andromeda's appearance, making it look heavier, more settled, more complete. Yet the Milky Way tells a quieter story, not because it is smaller, but because we are embedded inside it. From within, the galaxy's structure is harder to perceive. Dust clouds block our view, spiral arms overlap, distances blur together. What looks compact from the outside can feel endless from the inside. Beyond the stars lies the gas. Both galaxies are surrounded by vast reservoirs of hydrogen and helium, some glowing faintly, some completely invisible, unless observed through radio telescopes. Andromeda's gas disk extends farther than its stellar disk, wrapping the galaxy in a faint, diffuse envelope. The Milky Way has a similar structure, but its gas appears more fragmented, shaped by ongoing star formation and supernova explosions. Gas is important because it represents future potential. It is raw material. In this sense, Andromeda looks more mature, while the Milky Way looks more active. But none of this addresses the most important component of size: dark matter. Dark matter does not emit light, it does not absorb light. It does not interact with normal matter except through gravity, and yet it dominates the mass of both galaxies. For every kilogram of stars and gas you can see, there are several kilograms of dark matter you cannot. Each galaxy is embedded in a dark matter halo that extends far beyond anything visible. These halos are not neat spheres. They are lumpy, irregular, and dynamic. They contain substructures, streams, and concentrations shaped by billions of years of gravitational interaction. When astronomers measure the extent of Andromeda's dark matter halo, they find it reaches hundreds of thousands of light years outward, possibly more than 1 million. The Milky Way's halo is similarly vast. In fact, the two halos are so large that they already overlap. The space between the two galaxies is not neutral territory. It is a shared gravitational environment. This overlap changes how we think about size. If a galaxy's size is defined by where its gravity dominates over others, then Andromeda and the Milky Way are no longer separate objects at all. They are components of a larger system called the local group, bound together by gravity and moving toward a shared future. From this perspective, asking which galaxy is bigger becomes like asking which wave in the ocean is larger when both are shaped by the same tides. Still, astronomers try to quantify. Some measurements suggest Andromeda's total mass, including dark matter, is slightly greater than the Milky Way's. Other measurements suggest they are nearly equal. The uncertainty is not a flaw in observation. It is a reflection of how difficult it is to measure something that does not emit light and does not have clear edges. And size is not only about mass or distance, it is about influence. Andromeda dominates the local group. Many smaller galaxies orbit it. The Milky Way also has satellites, but Andromeda's gravitational reach appears stronger. Its past mergers have left long streams of stars arcing through its halo, evidence of galaxies torn apart and absorbed. These streams stretch far beyond its visible disk, marking territories where Andromeda's gravity once reached out and pulled smaller systems into itself. The Milky Way has similar streams, but fewer of them, suggesting a quieter merger history. This does not mean the Milky Way is smaller in the present. It means its past unfolded differently. Another way to think about size is through time. Galaxies grow, they accrete matter, they merge, they change shape. Andromeda appears to have assembled more of its mass earlier in cosmic history, while the Milky Way has been building more gradually. In the distant past, Andromeda may have been far larger relative to the Milky Way than it is today. In the distant future, the distinction will disappear entirely. Even now, the two galaxies are moving toward one another at hundreds of kilometers per second. This motion is not dramatic to the eye, but it is relentless. Over billions of years, it will erase their separate identities. Stars will not collide. Planets will remain largely unaffected, but the overall structure will transform into something new. Something larger than either galaxy alone. So how big is Andromeda compared to the Milky Way, really? It depends on what you are willing to count. Stars say one thing, gas says another. Dark matter says something else entirely. Gravity blurs boundaries. Time dissolves comparisons. Andromeda is bigger in light, possibly bigger in mass, certainly bigger in presence. But the Milky Way is not dwarfed. It is comparable, complex, and deeply connected to Andromeda in ways that make the question itself unstable. At cosmic scales, size is not a fixed number. It is a relationship, and Andromeda's true scale cannot be understood without the Milky Way standing beside it, moving with it, already sharing space with it, already shaping the same future. Another way to approach the comparison is to forget shape and brightness entirely and focus instead on motion. Galaxies reveal their true scale through how fast things move inside them. Stars far from the center should orbit slowly, if only visible matter were present. Instead, they move far too quickly. This mismatch is what first revealed the presence of dark matter, and it is also one of the most reliable ways to estimate a galaxy's true extent. In Andromeda, stars and gas clouds at extreme distances from the center continue to orbit at surprisingly high speeds. This means the galaxy's gravitational influence extends much farther than its visible disk. The same is true for the Milky Way. But when astronomers map these motions carefully, Andromeda's rotation curve stays flat for longer distances. That flatness suggests a halo that may stretch wider and contain slightly more total mass than our own. Yet this does not settle the matter. The Milky Way's rotation curve is harder to measure precisely because we are inside it. Distance estimates depend on parallax, Doppler shifts, and models of spiral structure that are still being refined. Small errors in distance translate into large uncertainties in mass. In some models, the Milky Way's dark matter halo rivals Andromeda's almost exactly. In others, Andromeda still wins by a modest margin. The difference is not dramatic, but it matters when we talk about dominance. Dominance, however, is not only about mass. It is about Andromeda's halo appears smoother and more extended, while the Milky Way's shows more irregularities. These irregularities are scars left by interactions with dwarf galaxies. Streams of stars stretch across our halo, remnants of systems that were pulled apart long ago. Andromeda has even more of these streams, some stretching tens of thousands of light years, wrapping around the galaxy like faint ribbons. These streams are important because they trace the outer boundaries of gravitational influence. Where stars are torn from one galaxy and captured by another, gravity has reached far beyond the visible core. In Andromeda, these traces suggest a more aggressive past, one where its reach extended deeper into surrounding space. Another subtle difference lies in thickness. Andromeda's disk is thicker than the Milky Way's, especially toward the center. This thickness hints at a history of mergers that heated the stellar orbits, puffing up the disk. The Milky Way's disk is thinner and more delicate, though it also contains a thick disk component made of older stars. Thickness is not size in the usual sense, but it reflects how much gravitational violence a galaxy has experienced, and therefore how much material it has absorbed. If you could step far outside both galaxies and look at them together, the contrast would be clearer. Andromeda would appear slightly broader, more uniform and more settled. The Milky Way would look more asymmetric, with irregular spiral arms and a less dominant bulge. Neither would look small. Both would dominate the darkness around them. There is also the question of satellite galaxies. Andromeda hosts a large population of dwarf galaxies, many of them tightly bound and orbiting in complex patterns. The Milky Way also has satellites, including the Magellanic Clouds, but Andromeda's system appears richer and more massive overall. These satellites add to the sense that Andromeda's gravitational influence reaches farther. Still, satellite populations are dynamic. Some of the Milky Way's satellites are on long, slow orbits and may not yet have completed a single circuit. Others are being torn apart even now. Andromeda's satellites show similar behavior. The difference is not absolute, but statistical. Then there is the question of future size. Size is not static. Galaxies grow by accretion and by merger. Andromeda is expected to continue absorbing smaller galaxies as time passes. So is the Milky Way, but the most important growth event for both lies ahead, not behind. As they move toward each other, their halos will interact more strongly. Gas will heat. Stars will be rearranged. The distinction between where one galaxy ends and the other begins will blur long before their visible disks touch. In a sense, both galaxies are already larger than they appear because their future selves overlap in space. From this perspective, asking which galaxy is bigger becomes a question about timing. At this moment in cosmic history, Andromeda may hold a slight advantage in visible size and total mass, but that advantage is temporary. In a few billion years, the concept of comparison will no longer apply. Even now, the difference is less important than the similarity. Both galaxies sit at the same scale of cosmic structure. Both are massive spiral systems shaped by dark matter. Both contain hundreds of billions to trillions of stars. Both exert influence across hundreds of thousands of light years. Both are products of the same physical laws acting over immense spans of time. Perhaps the most honest answer is this. Andromeda feels bigger because we can see it whole, while the Milky Way feels infinite because we are trapped inside it. One looks contained, the other feels boundless. But this is a trick of perspective, not a reflection of reality. When astronomers strip away light, distance, and bias, What remains is a picture of two galaxies so similar in scale that the differences fade into uncertainty. Andromeda may be larger in some definitions, the Milky Way in others. Neither clearly dominates in all respects. At the largest scales, size becomes a matter of influence rather than extent, of motion rather than shape. And by that measure, Andromeda and the Milky Way are already parts of the same system, already shaping one another's fate, already sharing a future that will erase the need for comparison at all. When we step even farther back and stop thinking in terms of appearance altogether, a different kind of comparison begins to emerge. This comparison is not based on what Andromeda and the Milky Way look like, but on how deeply they shape the space around them. At this scale, galaxies are not islands of light floating in emptiness. They are gravitational landscapes, carving slow pathways through the universe that everything nearby must follow. Gravity does not care about brightness. It does not care about spiral arms, glowing cores, or visible disks. It responds only to mass, wherever that mass may be, whether we can see it or not. And this is where the true size of both galaxies quietly reveals itself. Every star in the Milky Way is moving, not randomly, but along a path defined by the combined gravity of billions of other stars and an even larger amount of invisible matter. The same is true in Andromeda. When astronomers track how stars move at different distances from the centers of these galaxies, they find something unexpected. The farther out they look, the less the visible galaxy explains the motion. Stars far from the bright disk are moving too fast to be held in place by the stars we can see alone. This tells us that most of each galaxy's mass is not in its stars, but in an enormous, unseen halo that extends far beyond the glowing spiral. These halos are vast, diffuse, and difficult to define. They do not end abruptly. Their density simply fades slowly into the background of the universe. For both Andromeda and the Milky Way, these halos stretch hundreds of thousands of light years in every direction. In some estimates, they may reach more than 1 million light years across. That distance alone makes each galaxy many times larger than its visible form suggests, and because Andromeda and the Milky Way are only about 2.5 million light years apart, their halos are already overlapping, already interacting. This overlap is not dramatic, nothing collides, nothing lights up, but gravity is already being shared. Gas drifting between the two galaxies is influenced by both. Small galaxies in the region feel competing pulls. The local group, the collection of galaxies that includes both Andromeda and the Milky Way, is held together by this combined mass. From this perspective, asking which galaxy is bigger becomes increasingly subtle. Andromeda may have a slightly larger halo, or the Milky Way might. The uncertainties are large because dark matter cannot be observed directly. Astronomers infer its presence only through motion, and motion is shaped by time, history, and interaction. What matters more than exact numbers is that both galaxies operate at nearly the same scale. They dominate their region of space together. Neither one exists in isolation. Their true size is not just the space they occupy, but the space they influence. There is also a quiet asymmetry in how we experience these galaxies. Andromeda is something we look at from the outside. We see its spiral arms laid out clearly, its disk tilted gently toward us, its glow concentrated and defined. The Milky Way, by contrast, is something we look through. We are immersed in it. Its structure surrounds us, fragmented by dust and distance. Its size feels boundless, not because it is larger, but because it has no visible edge from our point of view. This difference in perspective affects intuition. Andromeda feels like an object. The Milky Way feels like an environment. One appears finite, the other feels infinite. But this is an illusion created by location, not by scale. If we could place ourselves far outside both galaxies and observe them together, the contrast would soften. Andromeda would still appear slightly broader, slightly more luminous at its center. The Milky Way would appear more irregular, with thinner arms and a smaller bulge, but both would be unmistakably comparable in size, mass, and complexity. Their histories help explain these differences. Andromeda appears to have experienced more mergers in its past. Evidence of this can be seen in long streams of stars orbiting its halo, remnants of smaller galaxies that were pulled apart and absorbed. These mergers likely contributed to its larger bulge and thicker disk. The Milky Way has also merged with smaller galaxies, but perhaps less frequently or in a gentler way. History matters because size is not static. Galaxies grow over time. They accumulate matter. They reshape themselves through interaction. Andromeda's current size reflects billions of years of gravitational encounters. The Milky Way's size reflects a different path through the same cosmic environment. There is also the matter of time moving forward. Both galaxies are still growing. Both continue to absorb smaller companions. Both continue to rearrange their internal structure through gravity. And most importantly, both are moving toward one another. This future changes how we think about present size. In a few billion years, Andromeda and the Milky Way will begin a slow merger. Not a violent collision, but a gradual blending. Their halos will fully merge first. Then their gas will interact. Then their stars will be redistributed into a new, larger galaxy. Long before any dramatic moment occurs, the distinction between them will already be gone. In that future, asking which one was bigger will no longer make sense. They will be part of the same structure. Their separate identities will dissolve into a single gravitational system that carries pieces of both histories forward. Even now, the seeds of that future are already present. The overlapping halos, the shared gravitational influence, the slow inward motion, all point toward a time when comparison gives way to unity. The universe does not preserve boundaries forever, it reshapes them. So how big is Andromeda compared to the Milky Way really?
It is slightly larger, invisible stars.
Possibly larger in total mass, certainly larger in some definitions of structure, but it is also similar enough that the difference depends entirely on how carefully you choose your definition. At the deepest level, both galaxies are expressions of the same underlying processes, operating at nearly the same scale, bound together by the same gravity, moving toward the same future. Size, at this level, is not a competition. It is a relationship. And Andromeda's true size cannot be understood without the Milky Way beside it, shaping it, responding to it, and eventually becoming one with it, long after the night sky we know today has faded into something entirely new. There is another way to understand the difference between Andromeda and the Milky Way that avoids numbers, almost entirely. Instead of measuring distance or mass, we can look at how each galaxy organizes itself internally, how orderly or chaotic its motion appears, and how stable its structure has been over time. At this level, size begins to feel less like a measurement and more like a pattern. Andromeda appears calmer than the Milky Way. Its spiral arms are more evenly defined. Its disk is smoother, with fewer abrupt distortions. Its central bulge dominates the inner region, giving the galaxy a sense of balance and symmetry. This does not mean Andromeda is peaceful. It means that much of its violent history happened long ago and the galaxy has had time to settle. The Milky Way feels different. Our galaxy is more irregular. Its spiral arms are patchy and fragmented. Star-forming regions flare brightly in some areas, while others remain quiet. Giant molecular clouds collapse, explode, and disperse in cycles that constantly reshape the disk. From within, the Milky Way feels active, restless, unfinished. This contrast is subtle but important. A galaxy that has grown larger earlier in cosmic history tends to look smoother later on. Gravity has had more time to redistribute energy, to circularize orbits, and to erase the sharp scars of past collisions.
In this sense, Andromeda's appearance suggests that much of its growth is already behind it.
The Milky Way, by comparison, may still be in a more active phase of its evolution. This does not make one galaxy superior to the other. It simply reflects timing. Size is not only about how much mass a galaxy contains, but about when that mass arrived. Early growth leads to stability. Ongoing growth leads to complexity and change. Another clue comes from the motion of stars above and below the galactic plane. In Andromeda, stars tend to orbit in more orderly paths with less vertical motion. In the Milky Way, many stars move in thicker, more chaotic layers, especially older stars that were stirred by past encounters. This thicker disk hints at interactions that heated stellar orbits, making the galaxy feel dynamically alive. These internal motions matter because they reflect how gravity distributes energy. A galaxy with greater mass concentrated early can absorb disturbances more efficiently. One that grows gradually may carry visible traces of each interaction for longer. In this sense, Andromeda's apparent smoothness may reflect not just size, but maturity. There is also the question of how each galaxy treats its outskirts. Andromeda's outer regions appear populated by stars that follow coherent streams, remnants of galaxies that were absorbed and stretched into graceful arcs. These streams trace Andromeda's gravitational reach far beyond its bright disk. The Milky Way also has stellar streams, but they are fewer and often harder to detect from our internal vantage point. These outer regions are where size becomes ambiguous again. The visible disk might end. Stars continue to orbit far beyond the bright spiral arms, bound by gravity to something that has no visible edge. When astronomers speak of a galaxy's virial radius, they are referring to this extended region of influence, not to something you can see. In both Andromeda and the Milky Way, this region is vast. It dwarfs the visible galaxy. It stretches into a realm where individual stars are sparse and distances between them are enormous. Yet gravity still holds them together, defining a structure that is more conceptual than visual. From this viewpoint, Andromeda and the Milky Way are less like objects and more like fields. They shape motion across space without needing to be filled with light. Their size is not where matter ends, but where order gives way to background randomness. This way of thinking also changes how we imagine the future. As Andromeda and the Milky Way continue moving toward each other, their internal structures will respond long before their disks overlap. Orbits will stretch, streams will distort. Outer regions will begin to align with a new shared center of gravity. In that process, size will lose its meaning entirely. The question will no longer be which galaxy is bigger, but how the combined system redistributes mass and motion. The future galaxy will inherit traits from both: Andromeda's smoothness, the Milky Way's complexity, and a scale larger than either alone. Even now, we are already living inside this transition. The Milky Way is not an isolated system drifting freely through space. It is part of a slowly evolving pair shaped by a neighbour whose influence extends far beyond what we see in the night sky. When we ask how big Andromeda is compared to the Milky Way, we are really asking how structure emerges, stabilizes, and eventually merges in the universe. The answer is not a number. It is a story told through motion, history, and gravity. And in that story, Andromeda is not simply larger or smaller. It is slightly ahead in one sense, slightly different in another, and deeply connected to the Milky Way in ways that make separation increasingly artificial. At cosmic scale, size is not a boundary, it is a relationship that evolves over time. And the closer we look, the more those relationships matter, far more than the measurements that first drew our attention. At the deepest level of this comparison, the idea of size begins to drift away from space entirely and settles into time. Galaxies are not just large because they stretch far across the universe. They are large because they exist across immense spans of cosmic history. Andromeda and the Milky Way are not frozen snapshots. They are ongoing processes, shaped by billions of years of motion, interaction, and gradual change. Both galaxies began as smaller structures in the early universe, assembling themselves from gas, dust, and dark matter shortly after the first stars ignited. Over time, they grew by pulling in surrounding material and by merging with smaller galaxies that wandered too close. Each merger added mass, altered structure, and reshaped internal motion. In this sense, size is inseparable from memory. A larger galaxy is often one that has lived through more encounters. Andromeda appears to carry a heavier memory. Its stellar population suggests that much of its growth happened earlier. Many of its stars are old, formed when the universe itself was younger. Its large central bulge hints at powerful mergers in the distant past, events that drove stars inward and reshaped the galaxy into a more settled form. Andromeda feels like a galaxy that gathered much of what it needed long ago and has been slowly evolving ever since. The Milky Way tells a slightly different story. It has also merged with smaller galaxies, but evidence suggests that its growth has been more gradual. Star formation continues actively in its spiral arms. Gas flows through the disk, collapsing into new stars, exploding as supernovae and recycling material in a steady rhythm. The Milky Way feels less finished, not because it is smaller, but because it is still deeply engaged in the process of becoming. This difference in timing affects how we perceive size. A galaxy that has already consolidated much of its mass can appear smoother and more coherent. One that is still actively forming stars and absorbing companions may appear more fragmented, even if its total mass is similar. Size in this sense is not just how much a galaxy contains, but how settled it is into its current form of base. Time also reveals why comparisons between Andromeda and the Milky Way are so uncertain. Measurements are taken at a single moment, yet galaxies evolve continuously. Small differences today may disappear tomorrow. A slight advantage in mass or extent is temporary, not permanent. Over cosmic timescales, these systems fluctuate, grow, and reshape themselves in ways that defy simple ranking. There is also the matter of future size, which is perhaps the most revealing comparison of all. Andromeda and the Milky Way are moving toward one another at a speed that feels slow on human timescales, but is inevitable on cosmic ones. In several billion years, their disks will pass through each other, their stars weaving together without collision, their gas clouds interacting, heating, and collapsing into new structures. Long before this happens, the question of which galaxy is bigger will lose relevance. Their halos will have merged fully. Their outer regions will respond to a shared gravitational center. The local group will become more unified, less divided into separate systems. The future galaxy that emerges will be larger than either Andromeda or the Milky Way alone, carrying the mass, stars, and history of both. Seen from that future perspective, today's comparison feels almost arbitrary. Asking which galaxy is bigger now is like asking which river is wider upstream when both are flowing toward the same ocean. The answer depends on where you stand and when you look, but the destination is shared. Even in the present, this shared destiny shapes how we should think about size. Andromeda's influence already extends into regions we consider intergalactic space. The Milky Way's gravity does the same. Their combined pull defines the structure of the local group, guiding smaller galaxies along vast orbits that take billions of years to complete. This means that both galaxies are already larger than they appear in isolation. Their true size includes not just what they contain, but what they control. Influence becomes as important as extent. Motion becomes as important as structure. From this angle, Andromeda is not simply a larger neighbour looming in the distance. It is a partner in a long gravitational relationship, one that began long before humans existed and will continue long after Earth itself is gone. The Milky Way is not a smaller, weaker companion. It is a comparable system shaped by similar forces, evolving along a path that happens to be offset slightly in time. The calmness of Andromeda's appearance and the restlessness of the Milky Way's internal activity are not signs of dominance or inferiority. They are signs of different phases in a shared cosmic life cycle. One has settled earlier, the other is still in motion. Both are immense beyond intuition. At this point, size becomes almost a metaphor. It reflects how much history a galaxy carries, how much influence it exerts, and how deeply it shapes its surroundings. Measured this way, Andromeda and the Milky Way are far closer than simple numbers suggest. The final insight is quiet but powerful. The universe does not organize itself into neat hierarchies of bigger and smaller. It organizes itself into relationships that change over time. Andromeda and the Milky Way are not competing structures. They are components of a larger process, already intertwined, already moving toward a shared future. So when we ask how big Andromeda really is compared to the Milky Way, the most honest answer may be this: Andromeda is big enough to shape our galaxy's fate, and the Milky Way is big enough to shape Andromeda's in return. Their true size is revealed not in isolation, but in the way they draw one another together across the quiet, patient flow of cosmic time. And in that slow convergence, size ceases to be a comparison at all. It becomes a story of connection, evolution, and inevitability, unfolding gently across billions of years. As the comparison stretches toward its quiet conclusion, one last shift in perspective brings everything into focus. Instead of asking how large Andromeda is compared to the Milky Way, it becomes more revealing to ask how distinct they really are. Because at the scale of galaxies, individuality is fragile, boundaries blur, identities soften. What feels separate on human timescales becomes continuous when viewed across billions of years. Both galaxies exist within the same gravitational environment. They are not isolated spirals drifting independently through the cosmos. They are members of the same family, embedded in a shared dark matter structure that defines the local group. This larger framework shapes their motion, limits their growth, and guides their long-term evolution. In this context, Andromeda and the Milky Way are less like separate objects, and more like regions within a larger gravitational system. This realization reframes size entirely. The Milky Way does not end where its stars become sparse. Andromeda does not end where its visible light fades. Both taper gradually into a shared background of influence. Their halos blend. Their satellite galaxies trace complex orbits shaped by both systems. Even the gas drifting between them responds to a combined pull. At this scale, size is no longer about ownership. It is about participation. Each galaxy participates in shaping the same region of space, the same flows of matter, the same future structure. Neither dominates completely. Neither recedes into insignificance. They coexist as comparable contributors to a single, evolving whole. This is why precise measurements continue to resist certainty. Astronomers refine estimates constantly, but the answer keeps shifting within margins of uncertainty. Not because our instruments are poor, but because the universe itself does not offer clean separations. Nature does not label where one galaxy definitively stops and the other begins. Even the language we use begins to strain. Terms like radius, edge, and boundary imply clarity that does not exist. What actually exists are gradients, density gradients, velocity gradients, gravitational gradients. And these gradients overlap extensively between Andromeda and the Milky Way. When we compare visible disks, Andromeda appears slightly broader. When we compare central bulges, Andromeda appears more massive. When we compare total mass, including dark matter, the two become remarkably similar. When we compare influence over time, the distinction nearly vanishes. This layered comparison reveals something deeper about how the universe builds structure. Large systems do not grow by filling space uniformly. They grow by accreting, interacting, and reshaping themselves through countless small changes. Size emerges from history, not from design. Andromeda's history happens to include more early mergers. The Milky Way's history happens to include more prolonged star formation. These differences matter, but they do not place the galaxies on different tiers of scale. They place them at different moments within a shared process. Even the coming merger does not represent an ending. It is simply another transformation. When Andromeda and the Milky Way finally combine, the resulting galaxy will not erase their histories. It will carry them forward, blended and redistributed. Stars will remember their origins through motion. Dark matter will remember through structure. Gas will remember through composition. From that future vantage point, looking back at today's comparison will feel almost quaint. Two spiral galaxies, once measured and contrasted, will have become one larger, quieter system. The question of which was bigger will dissolve into irrelevance, replaced by a new question about what the combined structure has become. This inevitability does not diminish the present, it deepens it. Knowing that both galaxies are temporary configurations within a longer flow of cosmic evolution makes their current forms more meaningful, not less. They are snapshots within a vast continuum, moments where gravity, matter, and time have arranged themselves in particular ways. In that sense, Andromeda's size is not something it possesses permanently. It is something it expresses right now. The same is true of the Milky Way. Their dimensions, masses, and structures are not fixed attributes. They are temporary outcomes of ongoing interaction. This is why the calm comparison works better than dramatic contrast. There is no need to declare one galaxy superior or dominant. The universe does not organize itself around winners, it organizes itself around balance and transformation. Andromeda is larger in some respects. The Milky Way is comparable in others. Both are immense beyond intuition. Both are embedded in a shared gravitational environment. Both are evolving toward a future where distinction gives way to unity. So when the question returns, how big is Andromeda compared to the Milky Way, really? The answer settles into something quieter than a number. Andromeda is large enough to shape our galaxy's destiny. The Milky Way is large enough to shape Andromeda's in return. Their sizes matter because of what they do, not because of where they end. At the largest scales, the universe does not ask us to compare objects. It invites us to observe relationships. And in the relationship between Andromeda and the Milky Way, size becomes a shared property, not a competition. What remains is not a verdict, but a recognition. Two galaxies bound together across space and time, already overlapping, already influencing one another, already moving toward a future where the question of size quietly fades away. And in that slow, inevitable convergence, the universe reminds us that the most meaningful dimensions are not measured in distance alone, but in connection, influence, and time. As this comparison settles into a broader view, one final layer quietly emerges, the layer that is easiest to overlook because it feels abstract, yet it shapes everything else. This layer is not made of stars, gas, or dark matter, but of probability. Galaxies are not only physical structures, they are outcomes among countless possibilities, shaped by small differences, amplified over enormous spans of time. Andromeda and the Milky Way began under similar cosmic conditions, both formed within the same expanding universe, from similar primordial material, governed by the same physical laws. Yet slight differences in their early environments set them on paths that gradually diverged. A nearby concentration of matter here, a slightly earlier merger there. A difference so small at the beginning that it would have been meaningless on human scales, but decisive over billions of years. This is why size comparisons feel slippery. The galaxies did not grow toward predefined targets. They grew by responding to what happened around them. Their present forms are not optimal solutions or final states. They are simply what emerged. In Andromeda's case, early mergers appear to have played a larger role. These encounters added mass quickly, reshaped the central region, and gave the galaxy a more dominant bulge. Over time, this early consolidation allowed the galaxy to settle into a smoother configuration. Its large-scale structure reflects stability achieved long ago. The Milky Way's growth unfolded more gradually. Instead of a few major early mergers, it absorbed smaller systems over a longer period. This slower accretion allowed star formation to continue actively in the disk, preserving thinner spiral arms and a more irregular internal structure. Neither path is better. Each is simply a response to different circumstances. This difference in history also affects how we perceive scale emotionally. Andromeda feels monumental, distant, complete. The Milky Way feels immersive, dynamic, endless. One feels like an object, the other feels like a place. That contrast has nothing to do with size in a strict sense. It has everything to do with perspective and experience. If humanity had evolved inside Andromeda instead, the Milky Way would feel like the distant smudge. Its spiral arms would appear graceful and contained. Its size would feel measurable. Andromeda, from the inside, would feel boundless and impossible to define. The roles would reverse completely. This highlights a deeper truth. Size is not an intrinsic property of a galaxy. It is a relationship between observer and structure. At cosmic scales, that relationship dominates intuition more than any measurement ever could. There is also a subtle psychological bias at work. Humans tend to associate brightness with importance and clarity with dominance. Andromeda's bright core and symmetrical disk align with that bias. The Milky Way's obscured center and fragmented view do not. But gravity does not care about clarity. It cares about mass. And mass, in both galaxies, tells a story of near parity. As observations improve, this parity becomes more apparent. Each new measurement narrows the gap rather than widening it. The more precisely we measure dark matter distribution, the more similar the two systems appear. The more satellite galaxies we discover around the Milky Way, the more it resembles Andromeda's entourage. The more we map stellar streams, the more both galaxies reveal complex overlapping histories. What once seemed like a simple hierarchy dissolves into a spectrum of similarity. This is not a failure of science. It is a success. It shows that the universe does not divide neatly into categories of bigger and smaller. It organizes itself through gradients and continuities. Andromeda and the Milky Way occupy the same tier of cosmic structure, shaped by the same processes, evolving under the same rules. Their impending merger reinforces this idea. The universe does not preserve separateness indefinitely. It favors combination. Over time, structures blend, redistribute, and reconfigure. Individual identities fade, but influence persists. From this long-term view, size becomes a temporary attribute. What matters more is trajectory. Where is a system headed? How is it changing? What relationships define its future? Andromeda and the Milky Way share a trajectory. They are moving toward a common center of gravity, toward a future galaxy that will inherit characteristics of both. In that future, stars from both systems will orbit together, indistinguishable in origin, except by subtle differences in motion and chemistry. That future galaxy will be larger than either Andromeda or the Milky Way today. But even then, it will not have a sharp edge. It will not end cleanly. It will extend outward through diffuse halos and faint streams, blending gradually into the larger cosmic web. This reveals the final lesson hidden inside the original question. When we ask how big Andromeda is compared to the Milky Way, we are really asking how the universe defines structure. And the universe's answer is quiet and consistent. Structure is not defined by borders, but by interaction. Galaxies are not containers, they are processes. Their size is not something they possess. It is something they express through influence, motion, and time. Andromeda expresses its size through early consolidation, a massive bulge, and a wide stellar disk. The Milky Way expresses its size through ongoing star formation, complex internal motion, and a vast immersive structure that surrounds us completely. Both expressions are valid, both are immense. In the end, the comparison leads us somewhere unexpected. Instead of revealing a clear winner, it reveals a deeper unity. Two galaxies, once thought of as separate giants, turn out to be variations on the same cosmic theme. And that theme is not about dominance or scale. It is about emergence, about how simple beginnings give rise to vast structures, about how time amplifies small differences into grand forms, about how gravity quietly arranges matter into patterns that feel eternal even though they are temporary. So, Andromeda is bigger in some ways. The Milky Way is comparable in others. But the most accurate statement may be the simplest one. They are big enough to shape one another, big enough to carry billions of stars, big enough to erase the need for comparison in the end. And in the slow movement of galaxies through space, That is the only scale that truly matters. As everything finally settles into place, one more quiet realization brings the comparison to rest. The universe does not rank its structures the way we do. It does not keep score. It does not preserve labels like larger or smaller beyond the moment they are useful. Those labels exist for observers trying to make sense of complexity from limited viewpoints. The universe itself simply allows structures to arise, interact, and transform. Andromeda and the Milky Way are products of the same rules playing out under slightly different circumstances. Their apparent differences are not signs of hierarchy but of variation. At this scale, variation is expected. No two galaxies follow identical paths, just as no two waves in the ocean are exactly the same, even when driven by the same tides. When astronomers zoom out far enough, both galaxies begin to lose their individuality. Their spiral arms blur into faint patterns. Their bulges fade into diffuse glows. Their halos merge into a shared gravitational background. From that distance, the distinction between Andromeda and the Milky Way becomes less important than the structure they form together. This is the level at which size truly dissolves. From here, the local group appears not as a collection of separate galaxies, but as a single gravitational region punctuated by concentrations of stars. Andromeda is one concentration. The Milky Way is another. Smaller galaxies drift around them like leaves in a slow-moving current. The entire system moves through the larger cosmic web, shaped by structures even more massive and remote. At this scale, the question of comparison no longer points inward, it points outward. How large are these galaxies compared to the filaments of the cosmic web? Compared to galaxy clusters? Compared to the voids that stretch across tens of millions of light years? Against that backdrop, both Andromeda and the Milky Way shrink into similar roles, comparable nodes within a much larger pattern. This does not make them insignificant, it places them in context. Significance in the universe is not absolute, it is relational. A galaxy is enormous compared to a star, modest compared to a cluster, small compared to the observable universe. Size shifts depending on what you place beside it. Andromeda feels immense when compared to the Milky Way from Earth. But together, both feel modest when placed against the scale of the cosmos. This layered sense of scale is what makes astronomy both humbling and calming. No structure holds center stage for long. Everything is part of something larger. Even the largest galaxies are temporary arrangements destined to merge, stretch, and fade into new forms. In this way, the eventual merger between Andromeda and the Milky Way is not a dramatic climax. It is a continuation, a natural step in a long sequence of rearrangements that began long before either galaxy had a recognizable shape. Gravity does not pause to acknowledge milestones. It simply carries matter forward into new configurations. From a human perspective, this future feels distant and abstract. Billions of years stretch beyond imagination. But from the universe's perspective, the timescale is ordinary. Galaxies merge the way clouds merge in the sky, slowly and without intention. When that merger happens, the resulting galaxy will not be Andromeda plus the Milky Way. It will be something new, shaped by both histories but belonging fully to neither. Its size will again be debated, its boundaries will again be uncertain, and observers, if any exist, will ask similar questions about where it ends and what it means. This repetition is not redundancy. It is the universe expressing the same principles at different moments. Structure arises, Structure interacts, structure dissolves into something else. Seen this way, the original comparison becomes less about resolving a curiosity and more about learning how to ask better questions. Instead of asking which galaxy is bigger, we begin to ask how galaxies function, how they grow, how they relate, and how they change. Those questions have no final answers, only evolving ones. Andromeda is larger than the Milky Way in some measures. The Milky Way rivals Andromeda in others. Both statements are true, and neither tells the full story. The full story exists only when we allow multiple perspectives to coexist. This is why astronomers speak carefully. They avoid definitive language not because they lack confidence, but because they understand how fragile certainty becomes at cosmic scales. The more deeply we understand the universe, the more we realize that simple answers rarely survive close inspection. There is something quietly comforting in this. The universe does not demand that we resolve every ambiguity. It allows complexity to exist without requiring resolution. Andromeda and the Milky Way do not need to be ranked to be understood. Their relationship is already meaningful without comparison. From the inside, the Milky Way will always feel infinite. From the outside, Andromeda will always feel immense. Both impressions are valid. Both are shaped by where we stand. In the end, the question of size gives way to a deeper appreciation of connection. These two galaxies are already part of each other's story. Their motions are linked. Their futures are intertwined. Their differences are details within a shared narrative. So how big is Andromeda compared to the Milky Way, really? It is big enough to reshape our night sky, big enough to alter our galaxy's future, big enough to remind us that scale is relative, boundaries are temporary, and structure is always in motion. And when we finally let the comparison rest, what remains is not a number, but a sense of belonging. Our galaxy is not alone. It is part of something larger, moving quietly through space, guided by gravity, time, and the same laws that shape everything else. In that vastness, Andromeda is not just bigger or smaller, it is connected. And that connection is the most meaningful measure of size the universe offers. As this long comparison reaches its deepest layer, the idea of size finally gives way to something even more fundamental: experience. Not human experience alone, but the way structure is experienced by anything that exists within it. Galaxies do not exist to be measured. They exist to host motion, interaction, and change. From the inside, scale feels different than it does from the outside, and this difference matters more than any diagram. Inside the Milky Way, size is not something we see all at once. It is something we move through. The galaxy reveals itself gradually, star by star, cloud by cloud, over distances so vast that they feel abstract. There is no moment when the Milky Way announces its full extent. It surrounds us continuously, shaping our sky, our motion, and even our sense of direction in space. In that sense, the Milky Way feels endless, not because it is larger than Andromeda, but because it contains us. Andromeda, on the other hand, exists for us as an image. We see it whole, compressed into a single faint glow. Its spiral arms are hinted at, its disk tilted delicately toward us. This wholeness creates an illusion of containment. It feels finite because we can hold it in our gaze, but that finiteness is deceptive. The moment we imagine entering Andromeda, travelling through its disk, moving between its stars, its size would unfold in the same overwhelming way our own galaxy does. This contrast reveals something important. Size is not an absolute property. It is a relationship between observer and structure. From the outside, a galaxy feels measurable. From the inside, it feels infinite. Andromeda is not truly smaller than the Milky Way simply because we can see it. We can see it because we are not inside it. If any civilization existed within Andromeda, its inhabitants would feel the same about their home. Their night sky would be filled with stars. Their galaxy would feel boundless. The Milky Way would appear as the distant smudge, the object that looks compact and manageable. The roles would reverse without changing the galaxies themselves at all. This symmetry strips the comparison of its emotional weight. Neither galaxy is privileged, neither occupies a special position. Both are vast environments experienced from different perspectives. The universe does not grant scale based on where observers happen to be. It grants scale through mass, motion, and time, regardless of who is watching. There is also a deeper lesson here about how the universe distributes complexity. Both Andromeda and the Milky Way exist at a scale where gravity allows long-term structure without freezing motion. Stars orbit for billions of years. Gas flows slowly. Change happens, but not so quickly that structure collapses, and not so slowly that nothing evolves. This balance is rare. It exists only at certain scales. At smaller scales, systems are too fragile. Planets change quickly, stars burn out. At larger scales, systems become diffuse. Galaxy clusters stretch across millions of light years, but individual structures lose cohesion. Galaxies sit at a middle scale where complexity can persist. Andromeda and the Milky Way both occupy this sweet spot. From this angle, their size is not impressive because it is large, but because it is functional. They are big enough to sustain structure, memory, and evolution over cosmic time. They are not so large that gravity smooths everything into uniformity, and not so small that chaos dominates. They are balanced systems. This balance explains why the comparison keeps resisting closure. There is no clean answer because both galaxies satisfy the same functional requirements. One does not dominate the other in the ways that matter most to the universe itself. Even the future merger reinforces this idea. When Andromeda and the Milky Way combine, the resulting galaxy will not suddenly become more important in any universal sense. It will simply move to a slightly different scale of balance. Star formation will change. Orbits will rearrange. Structure will evolve. But the same principles will continue to apply. In that future galaxy, size will again be debated. Observers will ask how large it is compared to other galaxies in nearby clusters. The cycle of comparison will repeat, not because it yields final answers, but because it helps observers orient themselves within vast systems. Orientation is the real purpose of asking about size. It is how minds locate themselves in relation to the universe. Andromeda feels large because it challenges our sense of place. The Milky Way feels infinite because it contains us. Neither feeling is wrong. Both are responses to scale, not measurements of it. This realization softens the original question completely. How big is Andromeda compared to the Milky Way, really? The answer is not a ratio, not a winner, not a conclusion. It is an understanding that both galaxies exist at nearly the same tier of cosmic organization, shaped by similar forces, bound by shared gravity and destined for the same long-term outcome. Their differences are real, but they are details within a broader similarity. Their sizes differ slightly depending on definition, but their roles in the universe are nearly identical. Both are homes for hundreds of billions of stars. Both shape vast regions of space. Both carry histories that stretch back almost to the beginning of time. At the largest scale, the universe does not care which one is bigger. It responds only to their combined mass, their shared motion, and the gradual unfolding of their interaction. The labels we assign fade, but the relationship remains. So when the comparison finally settles, what remains is not a verdict, but a perspective. Andromeda is not simply larger or smaller than the Milky Way. It is comparable in the deepest sense, comparable in influence, comparable in destiny. And that comparison leads somewhere unexpected. Instead of highlighting difference, it reveals connection. Instead of ranking, it reveals balance. Instead of measurement, it reveals belonging. The universe does not ask us to choose which galaxy matters more. It invites us to notice that both matter together as parts of a single, slow-moving story written across space and time. And in that story, size becomes less about how far something extends and more about how deeply it participates in the unfolding of everything else. That is where the comparison finally rests. As this exploration reaches its quiet conclusion, one final idea gently settles into place. The question of size, which seemed so clear at the beginning, has slowly transformed into something else entirely. It is no longer about which galaxy extends farther or contains more stars. It has become a reflection on how the universe organizes itself and how perspective shapes meaning. Andromeda and the Milky Way exist at a scale where certainty dissolves into approximation. Their measurements depend on how we choose to define edges that do not truly exist. Their masses depend on invisible matter we can only infer. Their structures depend on histories that are still being reconstructed. At this level, precision gives way to understanding. And understanding comes not from numbers alone, but from patterns.
What emerges from all of this is a sense of balance.
These two galaxies are not extremes, they are not outliers. They are representatives of a common class of structure in the universe, large enough to sustain complexity, small enough to remain cohesive, and dynamic enough to continue changing over billions of years. Their similarity is more striking than their difference. This balance is not accidental. It reflects the conditions under which galaxies form and survive. Too little mass and gravity cannot hold structure together. Too much mass and systems grow chaotic, dominated by mergers and violent rearrangements. Andromeda and the Milky Way sit comfortably in the middle, where structure can persist, evolve, and remain recognizable across vast stretches of time. This is why their comparison feels endlessly interesting, not because it reveals dramatic contrast, but because it reveals stability. The universe has found a scale that works, and it repeats it. Spiral galaxies like these appear again and again across the cosmos, each with its own variations, but all governed by the same quiet rules. From this broader view, Andromeda's slightly larger disk or brighter bulge becomes less important. The Milky Way's ongoing star formation becomes less exceptional. Both are expressions of the same underlying processes, unfolding under similar conditions. Their differences are real, but they are refinements, not divisions. Even their future merger fits this pattern. It is not an anomaly or a catastrophe. It is a natural outcome of proximity and gravity. Galaxies do not avoid one another when their paths cross. They interact, reshape, and combine. This is how larger structures form. The universe grows not by preserving separation, but by allowing connection. When Andromeda and the Milky Way eventually merge, the resulting galaxy will not erase what came before. It will carry forward the distribution of stars, the memory of motion, and the imprint of past interactions. Nothing is truly lost. It is redistributed. That redistribution mirrors the way this comparison itself has evolved. What began as a question about size has been redistributed into questions about influence, history, perspective, and destiny. Each layer added depth, not resolution, and that is fitting because the universe rarely offers final answers. It offers frameworks that continue to hold as understanding deepens. There is also something quietly reassuring in this. The universe is not built around sharp boundaries. It does not require us to choose between absolutes. It allows overlap, uncertainty, and gradual transition. Andromeda and the Milky Way overlap in influence. Their halos blend. Their futures converge. Their distinction is temporary. From within this vastness, our position feels both small and meaningful. Small because our galaxy is just one of many. Meaningful because it is part of a larger story of structure and connection. Knowing that our home galaxy has a counterpart so similar in scale and destiny gives context to our place in the cosmos. The night sky becomes richer when seen this way. That faint smudge of Andromeda is no longer just a distant object. It is a reminder that galaxies come in pairs, groups, and networks, that nothing truly exists alone, that even on the largest scales, relationship matters. So when the question returns one last time, how big is Andromeda compared to the Milky Way? Really, the most honest answer may be the simplest and the quietest. Andromeda is big enough to matter. The Milky Way is big enough to matter. Their size is not defined by comparison, but by connection. They are comparable not because they match exactly, but because they share the same role in the universe. They shape space around them. They host billions of stars. They evolve slowly. They merge eventually. They persist long enough for complexity to arise and meaning to be projected onto them. In the end, the universe does not ask us to decide which galaxy is larger. It invites us to notice how scale, perspective, and time transform simple questions into deeper understanding. And in that understanding, size becomes less important than belonging. Our galaxy belongs to a larger structure. Andromeda belongs to that same structure. Together, they remind us that even the largest things we can imagine are part of something larger still, and that realization, once it settles in, needs no further measurement. As the final layer of this comparison unfolds, the idea of scale dissolves almost completely, replaced by something quieter and more expansive. At this depth, the universe is no longer a place filled with objects of different sizes. It becomes a continuous fabric of structure, motion, and time, where distinctions exist only temporarily, and only for those who are close enough to notice them. Andromeda and the Milky Way, when viewed within this fabric, are not endpoints. They are transitions. They sit between smaller systems like star clusters and vastly larger systems like galaxy clusters, acting as bridges where complexity can persist without collapsing or dispersing. Their size matters not because it can be measured, but because it allows a certain kind of behavior to exist for a very long time. Within galaxies of this scale, stars have time to form planets. Chemical elements have time to build up through generations of stellar birth and death. Stable orbits persist for billions of years. Patterns repeat slowly enough to create memory, create. This is not guaranteed at all scales. It is a property that emerges only when gravity, time and mass are balanced in a narrow range. Both Andromeda and the Milky Way fall within that range. They are large enough to protect their internal structure from rapid disruption, yet not so large that violent mergers dominate every stage of their evolution. Their scale allows calm to coexist with change. This is why they feel so familiar when compared to one another, even though we observe them from radically different perspectives. From far away, they would look like twins separated by subtle differences. From within, each feels like a universe of its own. This duality reveals something profound about how the universe organizes meaning. At one level, Andromeda and the Milky Way are nearly interchangeable examples of spiral galaxies. At another level, they are unique environments shaped by distinct histories. Both descriptions are true at the same time. The contradiction exists only if we insist on choosing one perspective over the other. The universe does not choose. It allows both. This layered truth is why comparisons based on size alone eventually feel incomplete.
Numbers flatten nuance.
They compress rich histories into single values. They create the illusion of clarity where the universe offers continuity instead. Andromeda's slightly greater stellar count, its brighter core, or its broader disk are not declarations of dominance. They are outcomes of timing and circumstance. Likewise, the Milky Way's thinner arms, active star formation, and dynamic structure are not signs of lesser scale. They are signs of ongoing evolution. One galaxy appears settled, the other appears alive. In reality, both are alive. They simply express life on different rhythms. Time plays a central role here. Galaxies evolve so slowly that change feels invisible. Yet over billions of years, small differences accumulate into recognizable forms. The fact that Andromeda and the Milky Way are still recognizable as spirals at all is remarkable. Many galaxies lose that structure through repeated mergers. These two have maintained coherence long enough for comparison to remain meaningful. That coherence will not last forever. In the distant future, when the merger between Andromeda and the Milky Way has fully unfolded, the resulting galaxy will likely settle into a different shape. Its spiral arms may fade, its structure may become more elliptical. Star formation may slow. The calm balance that defines these galaxies today will give way to a new equilibrium. From that future vantage point, the question of which galaxy was larger will feel irrelevant. What will matter is that both contributed equally to something larger than either alone. Their individual sizes will be remembered only indirectly, encoded in the distribution of stars and the motion of the combined system. Even now, the seeds of that future are present, the overlap of halos, the shared gravitational influence, the slow inward drift. These are not dramatic events, but they are decisive ones. They remind us that separation is temporary, even at the largest scales. There is a subtle humility in this realization. Human minds are drawn to comparison because comparison creates hierarchy. It simplifies complexity into winners and losers, bigger and smaller, more and less. The universe does not operate this way. It favors continuity, transformation, and reuse. Andromeda and the Milky Way are not rivals. They are participants in the same long process. Their similarities are not coincidences. They are consequences of shared physical laws playing out under similar conditions. Their differences are not judgments. They are variations. Seen through this lens, size becomes an emergent property rather than a defining trait. It arises from interaction, history, and environment. It shifts as those factors change. It never stands still long enough to be absolute. This perspective also changes how we think about our place within the Milky Way. We often imagine ourselves as residents of a specific galaxy, as if that identity were permanent. In reality, our galaxy is a temporary configuration within a larger flow. The stars around us will eventually belong to a different structure. The sky above Earth will look different. The Milky Way itself will not remain the Milky Way. Andromeda's role in this transformation is not antagonistic, it is cooperative. Gravity does not fight, it combines. The merger will not erase the past, it will remix it. At this level of understanding, the original comparison dissolves completely. Asking how big Andromeda is compared to the Milky Way becomes less meaningful than asking how galaxies participate in cosmic evolution. Both galaxies answer that question in the same way. They grow, they interact, they change, and they eventually become something else. This is not a loss of identity. It is the natural progression of structure in a universe governed by gravity and time. Nothing remains fixed. Nothing is exempt. Even the largest things we know are part of an ongoing transformation. So the comparison reaches its quiet end, not with a conclusion, but with a recognition. Andromeda and the Milky Way are comparable because they share the same destiny. They are comparable because they occupy the same scale, where complexity can exist. They are comparable because neither stands alone. Their size matters not because it can be ranked, but because it allows them to play their role in the unfolding universe. And that role is not to be measured, but to continue, to hold structure for a time, to shape space quietly, to carry history forward. In the vast continuity of the cosmos, this is what size ultimately means. As the exploration reaches its final depth, what remains is not a comparison to be settled, but a feeling to be absorbed. The universe, when viewed long enough and gently enough, stops presenting itself as a collection of separate things and begins to feel like a single continuous process. Andromeda and the Milky Way are moments within that process, shaped by it and shaping it in return. At this level, size becomes almost symbolic. It no longer refers to distance or mass in any practical sense. It becomes a way of expressing endurance. A galaxy is large because it lasts. It persists long enough for patterns to emerge, for structure to stabilize, for complexity to arise and repeat. Andromeda and the Milky Way are large because they have survived the turbulence of the early universe and settled into long-lived forms. This endurance is rare. Many early galaxies formed quickly and disappeared just as quickly, torn apart by mergers or dispersed by gravitational interactions. Others never gathered enough mass to hold themselves together for long. The fact that Andromeda and the Milky Way still exist as recognizable spirals tells us that they occupy a stable region of cosmic possibility. They are not accidents. They are outcomes that the universe tends to produce under the right conditions. These conditions include not only mass and gravity, but environment. Both galaxies formed in a relatively quiet region of space, away from the dense cores of massive clusters where interactions are frequent and violent. This relative isolation allowed them to grow without being constantly disrupted. Their size is therefore tied to their surroundings as much as to their internal properties. Seen this way, Andromeda's slight differences in structure reflect subtle differences in environment and timing, not fundamental disparities in scale. The Milky Way's continued activity reflects a different rhythm, not a smaller role. Both galaxies are balanced within the same cosmic neighborhood, responding to the same large-scale forces. This balance is also why their future merger is so gentle in astronomical terms. The collision of stars will be rare. Most stars will pass by one another without ever noticing. The drama will unfold primarily through gravity, slowly reshaping orbits and redistributing matter. Even at this immense scale, change arrives softly. That softness is important. It reminds us that the universe does not rely on spectacle to transform itself. The most significant changes often happen quietly, over spans of time that dissolve urgency. Andromeda and the Milky Way are already changing one another, not through visible disruption, but through subtle gravitational influence that accumulates patiently. At this depth, comparison gives way to coexistence. The galaxies are not frozen entities waiting to be judged. They are evolving systems in conversation with their environment. Their size is a temporary expression of that conversation, one that will shift as conditions change. There is also a profound symmetry here. The same laws that shaped Andromeda shaped the Milky Way. The same gravity that holds our galaxy together holds Andromeda together. The same expansion of space that carries them apart on the larger scales brings them together locally. Nothing about their existence is exceptional in isolation. What feels exceptional is their relationship. That relationship is what gives the comparison meaning in the first place. Without proximity, without shared gravity, without an eventual merger, the question of which galaxy is bigger would feel trivial. It matters because these two structures are close enough to interact, similar enough to be compared, and significant enough to shape one another's futures. This is why the comparison resonates. It is not about numbers, it is about connection. From a human perspective, this connection is deeply calming. It suggests that even at the largest scales, nothing truly exists alone. Structures emerge together, influence one another, and eventually combine. Separation is temporary. Interaction is inevitable. Andromeda's presence in the sky is a reminder of this. That faint glow is not just a distant object. It is a preview of change. It is a sign that our galaxy is part of a larger story that continues whether we observe it or not. When we imagine the night sky far in the future, after the merger, the familiar band of the Milky Way will be gone. In its place will be a new, brighter structure spanning the sky in unfamiliar ways. Future observers, if any exist, will grow up inside that galaxy, feeling it as infinite, just as we feel the Milky Way now. They may look outward and see another distant galaxy and ask similar questions about size, scale, and comparison. The cycle will repeat, not because the answers were forgotten, but because perspective always resets the question. This repetition is not futile. It is how understanding deepens. Each comparison adds context. Each context reveals new relationships. The universe does not demand that we arrive at final answers. It invites us to keep observing. At the end of this journey, the original question feels softer, quieter, and more open. How big is Andromeda compared to the Milky Way? The question remains, but it no longer demands resolution. It has served its purpose by leading us through layers of scale, perspective, history, and connection. What remains is not a measurement, but an awareness. An awareness that galaxies are not defined by edges, but by influence. Not by isolation, but by interaction. Not by static size, but by evolving relationships. The Milky Way is large because it has endured. Both are large because they are part of something larger still. In the vast continuity of the universe, this is enough. As the final understanding settles in, the comparison reaches a place where even endurance gives way to continuity. At this depth, Andromeda and the Milky Way no longer feel like structures that persist against change. They feel like expressions of change itself. The universe does not hold on to forms forever. It allows them to exist long enough to matter, and then it carries them forward into something else. Galaxies at this scale are not monuments. They are currents. They flow through time the way rivers flow through landscapes, shaping and being shaped simultaneously. Their size is not an achievement. It is a consequence of motion unfolding slowly enough to be recognized. Andromeda's vast disk, its heavy central bulge, its extended halo, all of these are snapshots taken mid-flow. The Milky Way's thinner arms, active star formation, and complex internal motion are also snapshots taken at a slightly different moment along a similar path. The difference between them is not one of magnitude, but of timing. This realization removes the final trace of competition from the comparison. The universe is not presenting two candidates for judgment. It is presenting two variations of the same long process, caught at different phases. One looks more settled because more of its change happened earlier. The other looks more alive because more of its change is happening now. Even this distinction is temporary. Over enough time, the Milky Way will also settle. Star formation will slow, gas will be consumed or expelled, orbits will become smoother. Andromeda too will change again as it merges, redistributes and reshapes itself into a new form. What feels like maturity or youth today will blur into history tomorrow. This is why the universe does not privilege size as a final measure. Size is fleeting, influence fades, structure dissolves. What remains constant is process. At the largest scale, the universe is a system that allows structure to arise where conditions permit it. Andromeda and the Milky Way exist because their region of space allowed gravity to organize matter efficiently. Their similarity is not coincidence, it is inevitability under shared conditions. This perspective also clarifies why questions about edges and borders remain unresolved. There is no definitive place where a galaxy ends because ending would imply separation. Instead, there is a gradual thinning of influence, a slow blending into the surrounding medium. That blending is not failure, it is continuity. The halos of Andromeda and the Milky Way are not excess. They are the true form of a galaxy, revealed at low density. What we call the visible galaxy is merely the brightest part of a much larger structure. The faint outskirts, the streams, the diffuse matter. These are not accessories, they are essential. Seen this way, the galaxies are already less separate than they appear. Their outer regions are already part of the same environment. Their future merger is not a sudden event, but the culmination of a long-standing overlap. This overlap reframes how we think about presence. Andromeda is not approaching the Milky Way from afar. It has already arrived, gravitationally speaking. Its influence is already here. The Milky Way's influence is already there. The visible gap between them is not emptiness. It is a shared field. In this shared field, size loses clarity. What does it mean to say one structure is larger when both participate in shaping the same region of space? The distinction becomes semantic rather than physical. This is where the comparison gently dissolves. At the deepest level, the universe does not consist of isolated things with defined sizes. It consists of gradients of influence that overlap, interact, and evolve. Galaxies are peaks within those gradients, places where matter concentrates strongly enough to sustain long-lived patterns. Andromeda is one such peak. The Milky Way is another. Their peaks are similar in height, shape, and longevity. Their slopes overlap. Their bases merge. The landscape they form together is more meaningful than either peak alone. This landscape extends beyond the two galaxies themselves. It includes smaller companions, faint streams, drifting gas, and dark matter structures that bind everything together. The local group is not an assembly of separate objects. It is a single gravitational terrain with multiple high points. Within that terrain, asking which peak is taller misses the broader form of the land. This understanding also reshapes how we imagine cosmic significance. Significance does not belong to the largest structure or the brightest one. It belongs to structures that persist long enough to influence others. By that definition, both Andromeda and the Milky Way are deeply significant. They shape the motion of dozens of smaller galaxies. They define the flow of matter across millions of light years. They set the stage for future evolution. Their merger will not mark the end of that significance. It will extend it. The combined galaxy will shape an even larger region of space, guiding motion, hosting structure, and participating in the next phase of cosmic organization. From this viewpoint, size is not a ranking. It is a responsibility. A larger structure influences more space, more matter, more future outcomes. Andromeda and the Milky Way share that responsibility together. There is also something deeply calming in recognizing this continuity. The universe is not rushing toward conclusions. It does not discard structures abruptly. It allows them to transition gradually, preserving coherence as long as possible. The merger of these galaxies will take billions of years, not moments. Even change respects scale. This patience is the universe-defining feature. Everything unfolds slowly enough to be absorbed, studied, and understood, at least in principle. Even the most massive transformations are stretched across time until they feel almost gentle. Andromeda's apparent dominance or the Milky Way's immersive vastness are expressions of that gentleness. They are not extremes, they are stable configurations within a larger patient system. As the comparison reaches its quiet close, the question that once felt urgent now feels unnecessary, not because it has been answered definitively, but because it has revealed what lies beneath it. The universe does not invite us to choose which galaxy is larger. It invites us to notice how galaxies exist at all. They exist as long-lived flows of matter and motion. They exist as environments rather than objects. They exist as participants in a shared gravitational story that continues whether we observe it or not. Andromeda is not simply larger or smaller than the Milky Way. It is part of the same continuous structure. Their differences are real, but they are details within a broader sameness. Their sizes are impressive, but they are temporary. What endures is the process that formed them, sustains them, and will eventually transform them into something new. And when that process is finally allowed to speak without interruption, the need for comparison fades completely. What remains is a quiet recognition that the universe does not measure itself the way we do. It simply continues. As the scale of Andromeda continues to expand in the imagination, something subtle begins to shift, not in the numbers or the distances themselves, but in the way scale is understood. At first, size feels like a matter of comparison, this galaxy versus that one. One diameter placed beside another, one mass stacked against a second. But as the mind spends time with these proportions, scale stops behaving like a measurement and starts behaving like a condition, something that reshapes how everything else is perceived. Andromeda is not simply larger than the Milky Way in a linear sense. It occupies a different regime of structure. one where familiar ideas about separation, boundaries, and even isolation begin to lose their clarity. When two galaxies exist at this size, they are no longer isolated islands drifting independently through space. Their extended halos overlap long before their visible disks ever approach one another. Vast regions of dark matter, invisible but gravitationally dominant, interpenetrate silently, binding the galaxies together long before any star feels the pull of a foreign sun. From this perspective, Andromeda and the Milky Way are already interacting, already part of a shared gravitational system that stretches far beyond what telescopes can easily reveal. Within Andromeda itself, scale continues to unfold inward. Its central bulge contains hundreds of billions of stars, packed into a region so dense that stellar orbits overlap in complex layered motions. Light there does not travel through emptiness, but through a continuous haze of starlight, scattering, blending, and softening into a glow that never truly fades. This region alone contains more stars than many smaller galaxies combined, yet it is only one component of a structure that extends hundreds of thousands of light years in every direction. Beyond the bright disk lies something even more difficult to grasp: the stellar halo. This is not a sharp boundary, but a diffuse, ghostly envelope made of ancient stars, tidal streams, and remnants of smaller galaxies long since absorbed. These stars do not follow neat circular orbits. They drift on elongated paths, some plunging toward the center, others wandering far into intergalactic space before slowly turning back. The halo stretches so far that if it were visible to the naked eye, Andromeda would dominate the night sky, its faint glow covering a region many times larger than the full moon. This immense halo tells a story not of stability, but of accumulation. Andromeda did not form all at once. It grew by consuming others. Small galaxies approached, were torn apart by tidal forces, and their stars were scattered into long arcs that still remain detectable today. Each stream marks an ancient encounter, a quiet record of scale expressed not through explosion but through slow gravitational inevitability. Size, in this context, is not just magnitude, but history made visible. As attention shifts from structure to time, Andromeda's scale becomes even more striking. Light leaving its far edge today began its journey before complex life arose on Earth. Some of the stars we observe now no longer exist in their original form. Others have moved significantly along their orbits while their light travelled toward us. When observing Andromeda, distance and time collapse into one another, creating an image that is always slightly out of date, always a layered snapshot of many moments blended together. This blending of time becomes especially significant when considering the future. Andromeda is not moving away from the Milky Way like most distant galaxies. It is approaching, slowly, steadily, at hundreds of kilometers per second. The space between them is shrinking. This approach is not dramatic or sudden. It unfolds over billions of years, quietly altering the gravitational balance of the local group. Long before the galaxies collide, their outer stars will begin to feel each other's presence, their orbits subtly reshaped by an influence too distant to notice, yet too massive to ignore. When the eventual merger begins, scale again redefines meaning. There will be no explosion in the conventional sense. Stars are separated by such vast distances that direct collisions are extraordinarily rare. Instead, gravity orchestrates a slow dance. Spiral arms stretch and distort, gas clouds compress and ignite new waves of star formation. Over time, the distinct identities of both galaxies dissolve into a single, larger structure. Andromeda's greater mass ensures that the final galaxy bears more of its characteristics than those of the Milky Way, not because of dominance, but because scale determines outcome. Yet even this future event does not represent an endpoint. The merged galaxy will continue to evolve, absorbing smaller neighbours, reshaping itself under the influence of dark matter, and gradually transitioning into a more elliptical form. Scale does not freeze structures in place, it allows them to persist long enough to change slowly. Andromeda's size gives it endurance, not permanence. Stepping back further still, Andromeda's scale gains another layer of meaning when placed within the cosmic web. It is not alone. It is one node in a vast network of galaxies connected by filaments of dark matter and gas. These filaments stretch across millions of light years, guiding matter into dense knots where galaxies form and grow. Andromeda sits within one such filament, drawing material inward, shaping its surroundings over scales that dwarf even its already immense size. Compared to galaxy clusters, Andromeda is modest. Compared to dwarf galaxies, it is overwhelming. Scale is always relative, and Andromeda occupies a middle ground where complexity flourishes. It is large enough to host countless planetary systems, yet structured enough to maintain recognizable form. It is massive enough to shape its neighborhood, yet small enough to be shaped by larger cosmic forces. For the human mind, this balance is difficult to hold. Size at this level resists intuition. Numbers lose their meaning. Diagrams flatten reality. Even imagination struggles to stretch far enough. And yet Andromeda remains visible from Earth as a faint smudge in the sky. A reminder that extreme scale does not always announce itself loudly. Sometimes it appears quietly, requiring patience rather than awe to be appreciated. In this quiet visibility lies something important. Andromeda's size does not overwhelm perception through brightness or motion. It reveals itself slowly, through careful observation, through long exposure, through accumulated understanding. Its scale invites reflection rather than shock. It suggests that the universe's largest structures are not necessarily the most violent or dramatic, but often the most stable, the most persistent, the most patient. When compared to the Milky Way, Andromeda is larger, heavier, and more expansive, but not alien. Its spiral arms follow similar patterns. Its stars obey the same physical laws. Its dust clouds collapse under familiar pressures. The difference lies not in kind, but in degree. And that difference, multiplied over hundreds of thousands of light years, transforms familiarity into something vast enough to feel abstract. In the end, asking how big Andromeda really is leads to a deeper realization. Size at this scale is not a single number or dimension, it is a relationship between space, time, gravity, and history. It is the accumulation of countless small processes unfolding over billions of years, resulting in a structure so large that it reshapes how size itself is understood. Andromeda is not just bigger than the Milky Way, it exists in a regime where galaxies stop feeling like objects and start feeling like environments, places where scale becomes the defining feature, shaping everything within it without ever needing to announce its presence. And as it continues its slow approach across the cosmic dark, Andromeda carries that scale forward, unchanged by observation, indifferent to comparison, moving steadily toward a future where size will once again redefine what remains. As everything finally comes to rest, the idea of size no longer feels like something that can be concluded, only something that can be lived with. Andromeda's scale, once approached through comparisons and measurements, now settles into the background as a constant presence, something that exists whether it is named or not. At this stage, the galaxy is no longer an object under examination. It becomes a condition of reality, shaping space and time quietly, without requiring attention. What makes Andromeda feel so immense is not only how far it stretches, but how completely it alters the meaning of distance. Inside a galaxy of this scale, separation loses urgency. Light takes tens of thousands of years to cross regions that feel visually close. Stars that appear adjacent in the sky may be separated by hundreds of light years, moving through space on trajectories that will never intersect. And yet, gravity binds them all into a single, coherent motion. Scale here does not fragment the system, it holds it together. This cohesion is subtle. It does not rely on rigidity or permanence, it relies on balance. Andromeda exists because its mass is distributed in just the right way to prevent collapse while still maintaining structure. Too much concentration and the galaxy would become unstable. Too little, and it would dissolve into the background of the universe. Its size represents a narrow window where complexity can endure. That endurance carries implications beyond astronomy. Galaxies like Andromeda are long-lived enough to host multiple generations of stars, each enriching the galaxy with heavier elements. Over time, this slow chemical evolution allows planets to form, atmospheres to emerge, and conditions to arise that were impossible in earlier cosmic eras. Andromeda's scale is therefore not just spatial, it is temporal. It is a container for deep time. When the Milky Way is placed beside it in this context, the difference between the two feels almost ceremonial. The Milky Way shares the same capacity for endurance, the same balance between cohesion and change. Its slightly smaller mass does not diminish its role. It simply places it at a slightly different point along the same continuum. Both galaxies occupy a rare scale where the universe pauses long enough for structure to matter. This pause is deceptive. Nothing is static. Stars drift. Arms wind and unwind. Gas clouds collapse and disperse. Dark matter halos flex and respond to external influence. The stillness is an illusion created by time stretched so far that motion becomes gentle. Andromeda's scale allows motion to slow without stopping, creating a rhythm that feels calm rather than chaotic. As attention lingers here, another realization surfaces. Andromeda's size is not impressive because it is extreme. It is impressive because it is coherent. The galaxy holds together across distances so vast that human intuition breaks down, yet it does so without tension. There is no struggle at this scale, only persistence. Gravity does not strain, it simply operates. This quality reshapes how the future is imagined. When Andromeda and the Milky Way eventually merge, the event will not feel like a climax, it will feel like continuation. Two long-lived structures will become one longer-lived structure, carrying forward their combined histories into a new configuration. The resulting galaxy will not mark an end to size, but a re-expression of it. In that future, observers, if they exist, will grow up inside a galaxy formed from both Andromeda and the Milky Way. They will feel it as endless, just as we feel our own galaxy now. They will look outward and see other distant galaxies, faint and compact, and ask similar questions about scale and comparison. Perspective will reset, and size will once again become relative. This cycle reveals something essential. Size in the universe is not an absolute hierarchy. It is a sequence of perspectives layered across time. What feels immense from one position becomes ordinary from another. What feels distant from here becomes immersive from within. Andromeda is large not because it dominates the universe, but because it occupies a position where perspective transforms meaning. Placed within the cosmic web, Andromeda's role becomes clearer still. It is a node, a place where matter has gathered efficiently enough to persist. Filaments of dark matter and gas feed it slowly, guiding material inward across millions of light years. This feeding is not dramatic. It is continuous, almost imperceptible. Over time, it adds to the galaxy's mass, extending its influence and deepening its gravitational well. Compared to galaxy clusters, Andromeda is modest. Compared to dwarf galaxies, it is overwhelming. This middle ground is where galaxies like Andromeda and the Milky Way thrive. They are large enough to shape their surroundings, but small enough to maintain identity. They are neither fleeting nor frozen. This balance may be one of the universe's most important achievements. It creates environments where complexity can arise and persist without being immediately erased. Andromeda's scale is a manifestation of that balance. It represents a solution the universe returns to again and again across different regions and epochs. The comparison with the Milky Way ultimately reinforces this point. The two galaxies are not opposites. They are variations on a theme. Their differences reflect timing, history, and circumstance, not fundamental disparity. Andromeda's slightly greater mass and broader disk do not elevate it above the Milky Way in any cosmic sense. They simply place it slightly ahead in one evolutionary aspect. As this understanding settles, the original question begins to feel almost unnecessary. How big is Andromeda compared to the Milky Way? The question dissolves into a broader awareness of how galaxies exist at all. They exist as long-lived flows of matter and motion, stabilized by gravity, shaped by time, and guided by environment. Andromeda's scale teaches patience. It teaches that the most significant structures in the universe are not defined by sudden events, but by their ability to persist. It teaches that change does not need to be loud to be profound. It teaches that size is not something a structure claims, but something it grows into gradually. Even the faintness of Andromeda in the night sky carries meaning. A galaxy so vast appears so subtle from Earth, reminding us that perception is not proportional to reality. The universe does not announce its largest forms with spectacle. It allows them to exist quietly, waiting for attention rather than demanding it. When the mind finally releases the need to compare, what remains is a sense of calm continuity. Andromeda is large enough to matter. The Milky Way is large enough to matter. Both are part of a larger flow that does not require ranking or resolution. The universe does not ask us to decide which galaxy is greater. It asks us to notice that galaxies like these exist at all, that structure can persist for billions of years, that motion can be gentle at enormous scales, and that change can arrive without urgency. As Andromeda continues its slow approach, nothing dramatic announces its movement. The sky remains quiet. Stars continue their ancient paths, gravity continues its patient work, and size remains what it has always been at this scale. Not a boundary, not a competition, but a condition that allows the universe to keep unfolding. And in that unfolding, Andromeda stands not as an answer, but as an example of what happens when space, time, and matter align just long enough to create something vast, coherent, and enduring. There is nothing more for size to explain beyond this. The galaxy remains, and that is enough.